Okay, so is it visible to all of you? My screen is visible.
Yes, sir.
And by any
Yes.
chance, am I audible to you also? Because still lot of people have not turned on their camera, so perhaps I'm not audible to them. Is it the case?
You are audible, sir.
Okay, many people are not even responding also. Why are you there in the class? I don't know. Just putting proxy or what? Not turning on your camera, not responding anything. Out of 90, maybe some hardly 10-12 people, that's all. Okay, good. Happy to see few more faces. Fine, so let's start. This is 10th lecture for our course Digital Electronics and Circuits EN203, and we are discussing the realization of gates, basic gates through different technologies, and we have seen some basic technologies, for example diode logic, which can also be called as RDL, register diode logic. Then we have seen the RTL, register transistor logic. We have also seen DTL, diode transistor logic. So we have seen that there are some problems in all these different technologies, and that's why they were not so popular. So we have come to see what are the basic challenges with RTL technology, and we have seen that the output is very much load dependent, and if we try to reduce this R1 value to make it independent of load, then we are finding that lot of collector current is flowing, so which is not good for our other designs. So lot of power will be dissipated, and finally these cannot be overcome with the existing technology. And we are finding a contradiction in the requirement for the R1 or the collector resistance in the cutoff and saturation mode. So these two are demanding different values of R1. The cutoff mode is saying that R1 should be low, whereas the saturation mode is saying that R1 should be high. So they have different requirements. Now we try to manage that through another transistor, and that is where the new technology called as transistor logic comes up, where this the requirement for high resistance during saturation and low resistance during cutoff is managed through another transistor in series, you can say, or two transistors are connected on top of each other. So what we have basically, the basic principle what this is having is this totem pole structure. So this totem pole structure says that if one of the transistor is on, the other must be off, and if one of the other transistor is on, then the second one is on. So this must be follows in this must be followed in this structure, and then we can say that our output is not load dependent. It is perhaps dependent on what is the drop across the transistor and other components coming over there in the circuit. This we have seen, and based on this we have tried to come up with some way to turn on and turn off these transistors. So we have connected another branch over here with the same VCC voltage, and we see that whenever this transistor is off, it has the tendency to turn on this top transistor, and the bottom transistor in that case would be off. So whenever this transistor is off, we are getting the high output at the load terminal, and vice versa. Whenever this transistor is on, so we are basically turning on the bottom transistor along with that. So we have these two transistors getting turned on together, and so the output is at in low state. And what is happening to the top transistor, that because the voltage which is appearing at this base uh, terminal, that is not sufficient to break down this additional diode junction. So intentionally, that is why this diode is added, and so we do not trigger this transistor by mistake as well. So that is why something around 0.8 we are able to reach. However, we would need something around more than 1 volt to turn on this junction, at least. So this condition is met, and so we are happy that okay, our totem pole structure is working fine. Now for the input, what we have to give to this first transistor, that is on the extremely left hand side. So here, how to turn on this? One way could be you connect the base resistor and apply the input voltage and all that. That could be okay. There is no problem in that. But there is some better additions in this technology which make this more convenient even if we want to add some more inputs into this. So a structure like this, where this transistor, what I'm adding over here, has some special properties. So here the base is actually connected to VCC through a resistor R1, and the collector is actually connected to the base of this Q2, and the emitter is where it is receiving the input. So we have seen that if this input is low, which means there is tendency for this current to flow, the base emitter current, then this Q1 will go into turn on mode. It will go into saturation mode. And that is where the voltage over here across this transistor will remain at 0.3, and which is not sufficient to turn on this transistor. So as long as we are having low input, this transistor is off, which means this is also off, and here we have high output. So some kind of NOT operation is occurring over or happening over here. Am I clear? This point is clear to all of you, right? Now there is additional diode connected at the input terminal, that is to protect any negative voltage coming at the emitter. So if there is any negative voltage, this diode would conduct and there would be only maybe 0.6 volts available at the input. So it is safeguarding your circuit. Now when we apply high input to this circuit, just let me see where I have drawn. Okay, I think, yeah, the red color what we discussed over here. So yeah, if we apply any high voltage, then we see that this base emitter junction cannot be forward biased. And in that case, the current has tendency to flow from this base to collector and eventually turning on this transistor. So whenever this transistor is turned on, then we know that the output over here is going to be low because this will be on. So we have seen the case for even 2 volts also, not just the highest possible case 5 volt. We have seen even for the 2 volt case also, even if we assume that by chance it is conducting, eventually you will end up having a voltage at this point which will not be sufficient to make this junction forward biased. So you will end up having this transistor in turn off mode or cut off mode. So then other things would follow in the sequence. Am I clear up to this point?
Yes, sir.
Yes, sir.
Yes, sir.
So this special transistor can be seen as back-to-back diodes connected like this. But only for basic understanding, because once the base emitter junction conducts, you cannot say that this is something drop across this and drop across this. This is simply the saturation voltage 0.2 or 0.3 volts. So the behavior is not exactly like 2 diodes, but for basic understanding, you can assume that it is something like this. Is it fine?
Yes, sir.
Yes.
Good. Now there are some 95 people happy. At least we have crossed the half mark. 50% attendance is there at least. Good. Okay, so now we have also discussed that this transistor has certain special properties, that if we want to have more inputs, so this can be accommodated in form of multi-emitter transistor. So you can connect more inputs to the different emitter terminals available at this transistor. So that is why this is another speciality of the TTL logic or TTL technology. Now using this and the remaining circuit, we can very easily fabricate the NAND, NOR and some special gates as well. So as much as up to 8 inputs we can have in this form. Is that fine?
Yes, sir.
Good. Perhaps we will hit century now, 96. Let's hope. Okay, but I don't know. The cameras are going off suddenly. Okay, something has come up, some tea or coffee you want to share? Now, some people are indicating some things. I don't know whether their family members are asking what's going on. Generally, you don't attend classes. What is this? Something different is happening today. Hmm? Okay. Now, let us see how do we realize different gates. So let us draw and then identify what this circuit is doing. So what we will have first, we will start from the rightmost side. Let's have the totem pole structure first. So you need not remember it, no, memorize it. You can feel it that this is how the circuit is flowing. You need a totem pole structure because there is basic problem with RTL. Now, once you have this totem pole structure, you need something to drive it. What can drive it? There is another transistor which is having this kind of configuration where we have these connections given like this. Now, for this transistor to be driven, we have a special transistor and which is having multi-emitter kind of properties as well. And the collector is feeding the base of this driving transistor. Now we can have multiple inputs, for example, something like this. Now everywhere we have the protecting diodes. So let's say this is input A and this is input B. Everywhere this is VCC. And some resistance, of course, let's say load resistance, and then the output voltage is here. So you can put the numbers as per the sequence. So okay, maybe D1, D2, so this becomes D3, Q4. Fine, this is okay. Now what will happen with this circuit? What do you expect from the output? What do you expect? What will happen? Now you should be able to tell what this circuit is going to do. Yes? Okay, all the invisible people, perhaps I'm not able to see. Any response?
It's a NAND gate.
Okay, how? So Shiva is suggesting that it should behave like NAND gate. So how is that happening?
So because if one input is low, then output is high.
Yes. So the basic thing to understand over here is that even if one input is low, let us say this is connected to ground and this junction is broken, that moment we will find that the voltage across this is coming as VC sat. It doesn't matter if both are conducting or only one is conducting. Even if one base emitter junction is broken, this voltage appearing at this point would be only 0.3 volt, which means what? V out will be high. Understanding my point? Even if one input is low, the only condition for the output to be low is when both the inputs are high. This is the only condition when this output could be low. Am I clear or not?
Yes, sir.
Yes, sir.
Are you getting this? Any questions asked? Okay, numbers have started reducing. Perhaps some other things are there. 94 now. Okay. Ask questions. How that is happening? Are you clear?
Yes, sir.
Again, you may break this this transistor as combination of diodes like this. Even if one diode is conducting, the moment this transistor will come at its saturation voltage 0.2 volts or 0.3 volts, and then the voltage at this point at the base of Q2 will become 0.3 volts, which is not sufficient to make it conduct. Then we will get the high output over here. So our V out is behaving. So let's say this output is Z. So we can say Z is very much equivalent to A into B prime. That is the behavior of this gate. Are you getting my point?
Yes, sir.
So this would be the truth table of this. Fine. No doubts over here, right? Now how to realize the NOR gate? What to do? How to realize the NOR gate? Now what is NOR gate? So it says, let's say that is the output A plus B prime, isn't it? So what it is saying that if A, B and Z, if you write the truth table, what it would be, can you tell? What would be the outputs?
One zero
First
zero
one
zero.
and all other are 0.
Yeah, say again.
1
And all 0.
1110 or what? What are you saying? I'm not getting that.
1 0 0 0.
Okay, 1000. So what it is suggesting that even if one transistor is on or even if one input is high, you are going to get low at the output terminal. Are you understanding this? That is what this is suggesting, isn't it? Only when both the inputs are low, this is going to be high output over here. So how are we going to realize that? So what we do, we have the totem pole structure as it is. Now for driving, what we do, instead of one transistor, we have two transistors connected in parallel. And each transistor, this is driven by different set of this special transistor. Getting my point? What is happening over here? Now, even if one transistor conducts, okay, so what we have not done is connecting this. So even if one transistor conducts, what it will do? It will make this, okay, so if we name Q1, let's say Q1X, Q1Y, Q2X, Q2Y. So to simplify our understanding, and we have little bit matching also with that. So to make Q4 conduct, if either of this Q2 is this turning on, that is sufficient. Understanding my point? Even if one transistor out of Q1X or Q2Y, sorry, Q2X or Q2Y is conducting, then Q4 will conduct. And what will be the output if it conducts? Yes?
Low.
Yes. So
0.2.
correct. 0.2 volts, or this is low logic. So even if one of the transistors are getting turned on, this is going to be low. And that is what our truth table is also demanding. It is saying that even if one input is there, you have to have 0 at the output. So this is what it is doing. If you have any voltage, let's say either A or B or both having high voltage, more than 2 volts over here, this will not conduct. And if this doesn't conduct, then that means our Q2, one of the Q2 is conducting. And if one of the Q2 is conducting, or even if both are conducting, our Q4 is going to conduct, and then that's all. We are getting a low output over here. This is what the NOR operation that is happening over here. Am I clear? Any confusion in this? Yes or no?
No, sir.
No, sir.
So in terms of gate, we can make it like this, isn't it? This is fine. Now assume that if I extend another, because all these are special transistors, right? So if I extend one more input over here, let's say C over here, and some input D over here. You are understanding what I have done? I have added one input to this Q1X and another input at Q1Y. Now what will happen to this circuit? This was NOR, but now with 4 inputs, what it will do? Yeah.
Combination of AND, NAND and NOR.
Yes, yes, correct. Something very, very close. See, obviously the A and C inputs are going to have AND operation, isn't it? B and D are going to have AND operation. And this combined unit is going to have OR operation. And because this is behaving like NOT, so on top of that, there would be NOT operation, isn't it? So what your Z output would be, it would be A plus C, sorry, A into C plus B into D, and then NOT of this whole. This is what yesterday I mentioned as AND or inverted gate, AOI. This is another special gate which can be fabricated very easily with the structure, with the TTL structure. You can have more inputs over here. Understanding my point? This is how easy and convenient to work with TTL when we have such a special transistor or such a special things present over there. Fine. Any difficulty in this? Yes or no?
No, sir.
No, sir.
No means what? Nothing is clear or everything is clear? Yes?
Yes, sir.
Okay, you have to clarify what does this no means and yes means. No, this all very vague. Do you have any doubts? No, sir. That means two things are there. Either you have understood everything or you have not understood anything. In both the case, you don't have any doubt. Which one is true? Okay, I assume the first one. That is good for me. Fine. So now let us discuss some new technology that is called metal oxide semiconductor. And this is another type of transistor which is called field effect transistor. So these are some improvements over the BJT technology. So BJP is what? Bipolar junction transistor, where we have seen that the control action is due to the current flowing into the device, into the base. So this is what is driving this device into on state or off state and so on. So what happens that when you have continuous current flowing always into some device, obviously there are some power losses associated with that. And because of some other reasons, these devices are also slow in nature. So we are introducing another type of device where we have insulated gate, like there is no direct connection between the, so here this terminal is called gate. Another, this is control device. It has 3 terminals called gate, drain and source. And the control action happens over here because of the voltage applied at the gate, the VGS voltage. So it does not need continuous current flowing into the device for keeping it on. As long as this capacitor is charged, so this is kind of, that's why this gap is there. So a kind of capacitor is formed over here. As long as that capacitor is charged, this device will remain in the on state. And if you remove the control action, this will go into off state. Understanding my point? This is what is called the field effect transistor. There is something related with the applied field, the electric field what we are applying over here. And why we call this metal oxide semiconductor is because of its configuration. So how these are fabricated, this is not the typical way how BJT is fabricated. So let's say there are basically 2 different types of MOS devices. So one is called the PMOS, another is called the NMOS. So we will see what this is. Let's say this we are calling as PMOS and this we are calling as NMOS. What basically it means, the channel or the current which is flowing into this device, that is happening because of the positive charge carriers or negative charge carriers. That is what it indicates, the P or N. Now the PMOS is generally fabricated on N-type substrate. So you understand, right? N-type substrate, what I mean, right? There is a silicon, fabricate with this substrate is there, on which we are doing the doping with N-type of elements. That is fine, right?
Yes.
That's clear to you, right? Yes or no?
Yes, sir.
Yes, sir.
On this substrate, which is N-type, we are having some regions which are heavily doped with P+. P+ means heavily doped with the P-type substrates. So P-type elements. So now these are the 2 terminals. You can call them the drain and the source. Obviously, in this form, there is huge resistance offered by this path whenever you want to put a current through it, or let's say you apply in this a voltage across this, then so in this case it will be like this. So it will offer huge resistance in the path. So what we do, we put another terminal at this point to create the channel for the current to flow. So what we do, we put silicon oxide layer above this. So this is non-conducting silicon oxide. And then we put a metal. So let me make it red. Metal terminal, which we call as gate. So what we say that whenever this gate source voltage, because this is N-type substrate and P-type, P+ doping is over here. So we are basically looking for positive charge carriers in this device for the current to flow. So the voltage what we should apply over here, or the field what we should apply over here, should be a negative field to attract the charge carriers in this region. Understanding my point? So this gate source voltage should be less than some threshold value to make this device conduct. The current will start flowing between the drain and source if the gate source voltage is less than, so which is negative of this threshold value. So we need to apply some negative voltage over there. Understanding my point? This is what is called the PMOS. And if we draw this symbol for this MOSFET, that will be, you notice the arrow direction where I'm making. Source is connected to positive generally for PMOS, and drain is connected to the negative. And this is the gate. So the arrow is going inside. Understanding my point? That is the PMOS, field effect transistor. Now NMOS is exactly opposite of that. Exactly opposite means here it is P-type substrate. And then we have the regions formed with N-type doping. So heavily doped regions N plus are there. And then we are forming the channel in a similar way. What we are doing, again we are putting a layer of silicon oxide, which is the insulating layer, and then the metal on top of that for gate connection. So here we have gate source and drain terminals shown over here. Now here we need to accumulate the negative charge carriers over here. So we need to apply the gate source voltage more than the threshold value. A positive voltage must be applied between the gate and source to attract the negative charge carriers so that the current can flow whenever this field is applied. So this is called the NMOS type of FET. And here the symbol is having this arrow outside. And here the drain is connected to positive and source is generally connected to negative. So you are seeing that it's exactly inverted of whatever we have in PMOS. Am I clear? Yes or no?
Yes, sir.
This you have understood, right? This is a new type of device we are discussing. Okay, and we have understood that how to turn on this device, how to turn off this device. That is fine, right? There is no confusion in that. Now, let us see the characteristic of this device and how it behaves during the cutoff and saturation region. So let us take the NMOS device where we are applying the positive gate voltage. So the characteristic is actually very similar to BJT, except that there is no saturation voltage. The characteristic starts very close to y-axis. There is no gap between the y-axis and the characteristic. It is almost as if it is starting from zero. The BJT had a small gap and then it starts. So notice this difference. Here, this is what is responsible for VCE SAT. Here, there is no such thing. Understanding my point?
Yes, sir.
Yes, sir.
So depending on different voltages what you are applying at gate and source, this could operate in different positions. Again, similar to BJT, we have two regions where actually we want our device to operate, and that is the cutoff region and the saturation region. So this is where we call that this is our cutoff region, where VGS is less than the threshold value. So for simplicity, we keep VGS equal to 0. So then the device is off. There is no ambiguity in that. Then the other reason which you are seeing over here, which is kind of a very straight line kind of characteristic, this is what is our saturation zone. So here what is happening, that our gate source voltage is more than threshold. Threshold voltage is generally 2 volts to 4 volts, something like that. So this is what it is. Understanding my point? Now what this characteristic is suggesting us is that there is no VCE SAT. So in the cutoff mode, of course, it is like open switch or like a high impedance. Understanding my point? This is something like mega ohm kind of level. This is the cutoff mode. During the turn on, again, there is no voltage, there is no drop across this thing happening on account of like what was happening in the PN junction diode or BJT. So this is only straight line. What a straight line suggests that it is actually behaving like a resistor. So this value is called RDS on. This is during the on state or the saturation state. This value is actually very interesting to know that this is very much dependent on what we want to fabricate. So this can be varied from few milliohm to maybe few tens of ohms to maybe a kilo ohm also. And it all depends on what kind of fabrication or doping levels and all these things you are having. So basically based on the application, we make our MOSFET. Generally for power applications, we go for some milliohm range of MOSFETs. For our application where we have this gates and all this is of the order of some tens of ohm. So just like this, we fabricate and utilize in different circuits. Fine? Yes or no?
Yes, sir.
Yes, sir.
Clear? Now this is what we are going to utilize in making our circuits. So very simple and very similar to what we had in the RTL technology. So we can have some NMOS based gate. So a very simple NOT gate can be fabricated like this. You take an NMOS device, connect some high resistance, or high resistance is fine, or low resistance is also okay, because finally it is going to drive another FET only. So where the gate resistance is quite high, this is generally a capacitor. So it doesn't matter. This could be some high value. Now VDD. So whenever you apply any voltage A over here, this Z is simply not of A. Clear? So these gates are very easy to fabricate, very simple to fabricate, and because this is not drawing continuous power, so the power loss happening across this device is also low. So more and more gates can be packed together. So that is where we go into large scale integration or very large scale integration. So VLSI and all that is the origin. Like this is where it originates. Understanding my point? Am I clear? So
Yes.
based on this, if we can fabricate this NOT gate, we can have any other gate also, depending on how we are connecting. So this NMOS technology, we can connect two together. You give A input over here, B input over here, and okay, where to take the output? So make one resistance, connect it together, and here you take the output. So what this gate is? Any guess? What this circuit will do? Quickly. This is very simple to do, right?
NOR.
NOR gate.
NOR gate.
NOR.
You are asking or you are answering, Ashwin?
Sir, answering.
Okay. What is the answer?
Sir, NOR.
NOR. Okay. So he is suggesting something like this. Yash, what are you suggesting?
Sir, or.
What is that?
Sir, same no.
Okay, same NOR. Is it correct? Anybody having any different answer? Yes? So what it says basically that only when both the inputs are 0, A is also 0 and B is also 0, then only the Z is going to be 1. Even if 1 is conducting, the voltage over here would be low. Isn't it? Say something, yes or no?
Yes, sir.
Yes, sir.
That's fine, right? Now, if you have to make NAND gate, then so for NOR you had connected them in parallel. Now you can connect them in series. Now what is this? Even if any one is off, this is going to give 1. So that is the typical characteristic for the NAND gate. Even if any one is off, the VDD is going to appear over here. Only when both are on, this is going to be 0. Clear? Very easy to make, right? Yes or no? Quickly.
Yes,
Yes.
sir.
Okay. Now, interesting part is here. Even the resistance, what I am drawing over here, this itself is actually fabricated by a FET only, not by actual some register or something. This is also a FET which is connected in a special manner. So let us say if I draw the inverter, so the resistance part will be connected like this, VDD, and then this is your input and here is your output. So basically this connection means what? This is always on. And we have adjusted the RDS on in a manner that whatever we want, it will provide us. So on the same substrate, on the same silicon substrate, we can have all these realizations very, very easily. Later on, it is only connection. That's all. So that is how we can pack more and more things within the same chip area. So that is how we can do all the big fabrications or complex circuits on a very, very small size. Fine. So this is NMOS technology. Now quickly we can see what is CMOS technology. Again, that's also very, very simple. So again, as the name suggests, it's complementary MOS, which means we are utilizing both the PMOS and NMOS together for realizing this circuit. So this is CMOS logic. What it is doing, understanding my point? So we have a PMOS connected at the top and NMOS connected at the bottom. This is very much similar to the totem pole structure in the TTL logic. So what it says that whenever this one device will turn on, the other will be off. And whenever the first one is on, the second will be off. Understanding my point? How this is happening? So the A could either be 0 or 1, which means let's say you are applying some voltage of 0 volts or you are applying 5 volts, which is actually the VDD voltage. So when you apply 0 volts, what would happen? What would happen? Which one will turn on? Yes?
Sir, the PMOS.
PMOS. Why?
Sir, VGS will be positive.
VGS will be negative actually. When you apply 0 voltage at the gate and your source, please mind that here it is opposite. The source is here, drain is here. For the NMOS, the drain is here and source is here. Understanding my point? So whenever you are applying 0 volts at the gate, your VGS voltage is becoming how much? -5. Because your source is at 5 volts. And with the negative voltage, this PMOS device will turn on. And with the 0 voltage over here at for the NMOS device, this will be off. So the output will be the inverted A. Fine. Yes or no? Say something.
Yes, sir.
Clear. Now, if you have this VGS voltage, sorry, this at A, if you apply 5 volts, what would happen to the PMOS VGS? This will go to 0. And what will happen to NMOS VGS? This will be at 5 volts. So this will be off and this will be on. So your output will come down to low. So this is the inverter, what you have realized using the CMOS technology. Any confusion? Simple. Whatever rules we have stated, we are following exactly that. Nothing additional. Whenever this gate source voltage is less than the threshold value, this PMOS is and negative, then this PMOS is going to be on. And whenever this gate threshold, the gate source voltage is going to be more than the threshold, positive voltage, then the NMOS is going to be on. That is the simple rule. With that, you can understand this. Nothing very difficult in this. Now, if we have to fabricate the NAND and NOR gates using this CMOS technology, again, that's very, very simple to do. So let me draw the circuit first and then ask you the question what that is. So, okay. We have the PMOS at the top. So let's say this input is A, this input is B. Similarly, this input is A, this input is B. And this V out we are talking about, which is Z. So what is this gate? What we have realized? Can you answer? Yeah.
Sir, NAND gate.
Okay. Is that correct? Is that correct? Anyone having any different answer?
No, sir, same.
Yes or no?
NAND gate.
Okay. Let us see the other one. Here I connect the PMOS in series and the NMOS in parallel. Okay, now what is this?
NOR gate.
Yes. Is that fine? So easy to understand and easy to fabricate, and because of low power dissipation, high speed and all, so many chips can be, so many devices can be packed within a small chip area. So that is the beauty of this technology CMOS, and because of this we have been able to pack lot of bigger devices in a very small package. So this concludes the design of gates based on different technologies what we have done. So any questions if you have, you may ask. Some things I have left out, which perhaps in the tutorial tomorrow I can discuss, so that that can also be covered. But I feel this is more than sufficient for you, where you have understood the basic principles behind how different technologies are operating and how different gates are fabricated. So now onwards, we can go on and design some bigger circuits, bigger digital circuits, where we will be using some minimization techniques and some more realizations. So those things we will be doing. So any questions up to this point? So tomorrow onwards, again, we will start our switching functions, and we will see what can be done. It's fine, right? No questions further?